Most people assume the biggest mistake in a solar system is choosing the wrong panel. In reality, some of the largest performance losses can come from the cheapest component in the entire package. And once you understand how many so-called complete solar kits are designed, you'll never look at the included wiring the same way again. The word complete creates a powerful impression because it suggests confidence, compatibility, and the comforting idea that someone else has already handled the engineering. You buy the kit, bolt the parts together, connect a few cables, and begin collecting energy from the sun. That is the promise most people see. Hidden inside that promise is one assumption many buyers never stop to question. They believe every component inside the box was chosen because it delivers the best performance in real-world installations, instead of simply being the most economical way to build a competitively priced kit. This is not about claiming every solar kit is a scam. There is no verified evidence of an industry-wide effort to mislead customers, and the reality is much more practical than that. Many budget kits are designed around ideal installation conditions, including very short cable runs, specific current levels, and little expectation that the system will grow later. The problem is that very few real installations stay within those original assumptions. Batteries often end up farther away than planned. Charge controllers get relocated, inverters move to improve ventilation, and many owners decide to add more panels months after the original installation. None of those changes seem dramatic, yet each one changes the electrical demands placed on the wiring. A cable that worked perfectly in the manufacturer's intended layout can quickly become one of the weakest parts of the entire system once those conditions change. That is where this discussion really begins. Instead of focusing on expensive batteries or flashy solar panels, we're looking at one of the most overlooked parts of a DIY solar installation, the wiring included inside those complete solar kits. More importantly, we'll cover 7 warning signs that should make you stop before assuming those cables are actually right for your system. The first warning sign begins with something most people never think about. Distance. When beginners look at a wire, they usually ask whether it can carry enough current. That sounds like the right question, but it only tells part of the story because electrical systems care just as much about resistance. Every conductor has resistance: premium cable, budget cable, thick cable, thin cable. None of them are completely free from it. Electricity always pays a small price as it travels through a wire, and that price shows up as resistance. Resistance creates two things every solar owner wants to avoid: voltage drop and heat. As the distance increases, resistance increases with it. In simple terms, doubling the cable length roughly doubles the voltage drop, which is why experienced installers don't begin by asking what gauge wire they're using. They start by asking how far that wire has to travel. A cable that performs perfectly across a short connection can tell a completely different story after the battery bank is moved, or the charge controller ends up several feet farther away. Nothing about the wire has changed. The installation has. That simple change is often where expectations begin to separate from reality. The phrase complete kit encourages buyers to believe the included cables are suitable for every situation, while in practice those cables are usually selected for one specific installation scenario. The moment your layout differs from that original plan, the electrical calculations change and physics never adjusts itself to match the marketing. One of the most common mistakes isn't buying poor quality equipment. It's trusting good equipment connected by wiring that was never designed for the way your system is actually installed. The difficult part is that everything can appear perfectly normal. Your panels still generate electricity, the charge controller still powers up, the battery still charges, and nothing looks obviously wrong. Hidden losses rarely announce themselves with warning lights. Instead, they quietly steal efficiency a little at a time until the performance gap becomes significant. That leads directly to the second warning sign: small battery cables. Few areas of a solar system are underestimated more often than the wiring connected to the battery. Many inexpensive kits include battery cables in sizes like 10 AWG, 12 AWG, 14 AWG, and sometimes even 16 AWG. Those cables can absolutely be appropriate. They work well in smaller systems over short distances and under the specific conditions they were selected for. The mistake happens when people assume that because those cables came inside the box, they must also be correct for every installation they build. That is a completely different assumption. Battery cables often carry some of the highest current found anywhere in the system, and as power demands increase, those conductors become far more important than many beginners realize. Current has an interesting characteristic because its losses don't increase in a straight line. Engineers often describe the relationship as current squared multiplied by resistance, but the practical lesson is much easier to remember. Double the current and the losses increase 4 times. That is exactly why current deserves so much respect. It also explains why low voltage systems often require surprisingly thick conductors. At first glance, that seems backwards because lower voltage sounds like it should require smaller wiring, yet the opposite is usually true. Lower voltage means higher current is needed to deliver the same amount of power, and higher current demands larger conductors if you want to keep voltage drop under control. The difference becomes obvious when comparing common system voltages. Imagine a 1000 watt load. On a 12 volt system, that load requires roughly 83 amps before efficiency losses are considered. Move the exact same load to a 48 volt system and the current drops to roughly 21 amps before efficiency losses. The power stays exactly the same. The current changes dramatically. That single comparison explains why 12 volt systems are much less forgiving when cable sizing is overlooked. The wiring isn't simply connecting components anymore. It's carrying substantially more current to accomplish the same task, which means every decision about conductor size becomes far more important. Many first-time builders are surprised when they discover the solar panel isn't always the limiting factor. Sometimes the battery cable becomes the silent bottleneck instead. Once that pattern becomes clear, another design choice starts making a lot more sense, and the next warning sign appears in one of the most exciting components found in almost every solar installation. The inverter. This is the device that converts stored DC power into the AC electricity your household appliances actually use, so buyers naturally focus on the number printed across the front: 1000 watts, 2000 watts, sometimes much more. That number only tells half the story. The other half is the amount of current flowing between the battery and the inverter. As we just covered, a 1000 watt inverter connected to a 12 volt battery can draw roughly 83 amps before efficiency losses. That is an enormous amount of current compared to many other parts of the system, which means the wiring must safely carry that load while keeping voltage drop as low as possible. One complaint that appears repeatedly throughout DIY solar communities involves inverter cables that feel much smaller than owners expected. That alone doesn't prove the manufacturer made a mistake. Those cables may be completely suitable for a short installation built exactly as the kit was originally intended. The problem begins when owners unknowingly change those original conditions. The inverter might be mounted farther away for better airflow. The battery bank could end up in another compartment. Months later, extra equipment gets added to the system. Nothing looks dramatically different from the outside. Electrically, almost everything has changed. More distance creates more resistance. More resistance creates more voltage drop. More voltage drop means the inverter may no longer receive the voltage it expects to see. One of the most frustrating parts is that the inverter itself often gets blamed first. Owners start seeing low voltage alarms, unexpected shutdowns, or reduced output, and naturally assume the inverter is defective. Others point to the battery or even the solar panels, while the actual problem is sitting quietly between those components in the form of wiring that no longer matches the installation. Wires rarely attract attention, so they are often the last thing people investigate. That mistake slips by for another reason. Unlike a cracked solar panel or a failed charge controller, undersized wiring doesn't always fail in a dramatic way. Most of the time it keeps working while quietly reducing performance. That brings us to the fourth warning sign: power that never reaches your battery. When people think about solar efficiency, they usually picture cloudy weather, dirty panels, or shade from nearby trees. Very few imagine the cable itself consuming part of the energy their panels produce. Resistance doesn't make electricity disappear. It converts part of that energy into heat. That is what voltage drop represents. Instead of reaching your battery, a portion of the energy is lost along the path as heat inside the conductor. Industry guidance commonly recommends designing important DC circuits around roughly a 2% voltage drop, while about 3% is often treated as a practical upper design target. Those percentages sound small. Over the lifetime of a solar system, they are anything but. Even modest losses repeat every day the system operates, and unlike changing weather conditions, they never stop. There are field examples that show how noticeable those losses can become. One widely discussed example described a 150-foot run of 10 AWG wire carrying roughly 30 amps on a 48-volt system. According to that example, approximately 270 watts were being lost as heat, or around 15% of an 1800-watt solar array. That example is anecdotal rather than a controlled study, but it illustrates an important principle. Wire sizing isn't only about keeping a system safe. It's also about protecting the energy you've already paid to generate. That distinction matters because many beginners think of cables in simple terms. They assume a wire is either safe or unsafe. Experienced installers evaluate two completely different questions. Can the conductor safely carry the current? Will the voltage drop stay within an acceptable range? Those are not the same calculation. A cable can satisfy one requirement while falling short on the other. That is why looking only at ampacity creates a false sense of confidence. Ampacity refers to the maximum current a conductor can safely carry, and it depends on factors such as insulation, temperature, installation method, conductor material, and how the cable is installed. Efficiency is a different conversation. Ampacity alone cannot tell you whether your system is wasting energy through unnecessary voltage drop. Ignoring that second calculation is one of the easiest ways to build a solar system that technically works while quietly giving away performance every single day. At this point, an obvious question comes up. If larger cable usually performs better, why don't manufacturers simply include thicker wiring in every kit? The answer is straightforward. Copper is expensive. Heavier cable costs more to manufacture, more to ship, and often requires larger connectors as well. Every increase in conductor size raises production costs, especially in entry-level products competing on price. None of that proves manufacturers are trying to deceive customers. There is no verified evidence supporting that claim across the industry. Cost optimization is simply part of product design. When companies build affordable solar kits, every component is reviewed to keep the final price competitive. The wiring is no exception. Looking at it that way, the included cables begin to make much more sense. They are often selected for the configuration the manufacturer expects customers to build, not every possible installation someone might create months or years later. That is where expectations and reality start moving in different directions. The manufacturer designs for one layout, the customer builds another. As those two situations become less alike, choosing the proper wire size becomes increasingly important. The final warning sign isn't a particular cable, it's a particular mindset. If it came in the box, it must be the right choice. That assumption is completely understandable. The product is advertised as a complete kit, so most buyers naturally expect every component to be fully optimized for any installation they have in mind. Experienced installers approach the situation differently. They don't start with the cable that arrived inside the package. They start with the installation itself. They calculate how much current will actually flow, how far that current must travel, which system voltage is being used, what level of voltage drop is acceptable, and whether the system is likely to expand in the future. Those answers determine the wire. The packaging does not. Professional guidance consistently recommends sizing conductors according to system voltage, maximum continuous current, total cable length, acceptable voltage drop, and applicable electrical code, rather than simply copying the cables included with a low-cost kit. Ironically, many expensive upgrades happen because someone trusted the least expensive component. A larger battery gets installed, more solar panels are added, more powerful inverter replaces the original one. Only then does the owner discover the original wiring no longer matches the system sitting in front of them. The result is buying the cables twice. Once inside the kit, then again after learning what the installation actually requires. This pattern appears again and again throughout DIY solar communities. Builders discover unexpected voltage drop, Battery cables turn out to be smaller than the current they're carrying. Really demands. Long extension runs reduce charging performance. More experienced users eventually recommend moving to thicker conductors after the entire installation is already finished. Those stories don't prove every solar kit is flawed. They reveal something much more valuable. Many people misunderstand what the word complete actually means. Complete doesn't automatically mean optimized. Complete doesn't automatically mean future-proof. Complete doesn't automatically mean the best choice for your specific layout. There is one final detail that's surprisingly easy to overlook. Most buyers become obsessed with upgrading their solar panels because those are the most visible part of the system. They compare efficiency ratings, frame construction, and cell technology, while the cable connecting those expensive components receives almost no attention. Every watt your panels produce still has to travel through that conductor. If the path isn't designed correctly, part of that energy never reaches its destination. Not because the panels failed, not because the battery was defective, not because the charge controller stopped working. It happens because electricity always follows the same rules. Current, resistance, distance. Those principles never change because a product description sounds reassuring. They never change because the packaging says complete. They never change because the included cable happened to fit inside the box. That is why experienced solar buyers don't judge a kit by the list of parts inside it. They judge it by the assumptions those parts were selected around. Understanding those assumptions often makes the difference between a system that simply functions and one that performs at its full potential for years. The biggest mistakes in solar rarely come from buying the wrong technology. They usually come from assuming someone else has already done every calculation for your installation. Manufacturers can only design around the configuration they expect. Your installation is the one that determines whether those assumptions still hold true. Battery mounted a little farther away, an inverter relocated for ventilation, or additional panels installed months later can completely change what the wiring needs to handle. The equipment may stay exactly the same. The electrical demands do not. That is why professional installers work backwards from the installation instead of forwards from the contents of the box. They calculate the maximum continuous current. They measure the total cable length. They account for the system voltage. They decide how much voltage drop is acceptable. Only after those questions are answered do they select the conductor. The wire is the result of the calculation. It is never the starting point. Looking at a solar kit through that lens changes the way every component is evaluated. Instead of asking whether the included wiring is good or bad, the better question is whether it matches the system you're actually building. Sometimes the answer is yes, sometimes it isn't. Knowing the difference can save both money and frustration later. Replacing a cable during installation is usually simple. Replacing it after everything has already been mounted, connected, and expanded is a very different experience. That is why planning ahead matters so much. Even if your system is small today, there is always the possibility that it won't stay that way. Many solar owners eventually add another battery. Many install more panels. Many upgrade to a larger inverter. Planning for realistic expansion from the beginning can prevent expensive rewiring later. The irony is hard to ignore. People willingly spend hundreds or even thousands of dollars upgrading panels, batteries, and inverters, yet hesitate when it comes to investing in the conductors that connect every one of those components together. Those conductors determine how efficiently power moves through the entire system. Without the right wiring, every other upgrade has less opportunity to deliver its full benefit. That doesn't mean every installation needs the largest cable available. It means the cable should match the electrical demands of the installation instead of simply matching what happened to come inside the package. Small pieces of copper rarely receive much attention. Even so, they influence every watt flowing through the system. Understanding that simple fact changes the way you evaluate any complete solar kit. Instead of assuming every included component is automatically the perfect choice, you begin asking whether those parts were selected for your installation or for a different set of assumptions. That shift in thinking is what separates simply assembling a solar kit from truly understanding how the entire system works together. The future of residential and off-grid solar won't belong to the people who own the most equipment. It will belong to the people who understand how every component interacts with the others and who recognize that sometimes the smallest piece of copper determines whether the entire system reaches its full potential.